number of pixels. And finally, locality. And locality means that the description of the feature is dependent upon a neighborhood, but not too big a neighborhood. If you remember, one of the reasons we said that is that if the neighborhood is too big, then if I change my viewpoint a little bit and something's occluding part of that, even though I can still see the feature, the neighborhood might have been partially occluded, and then the feature might not be detected anymore or not described the same way. So locality means that I want a descriptor based upon a region around it, but not too big a region. All right, so fundamentally, in terms of what makes a good feature, we need to talk about finding one and describing one. And today, we're going to talk about the notion of finding these features, sometimes referred to as interest points. And these are going to be defined to be the points in the image that would likely make good features, that is, ones that satisfy all those criteria we just talked about. So let's start thinking about an image pattern. And imagine you're looking at a large black square against a white wall. Okay? Would the middle of the square be a good interest point? Megan, what do you think?
Yes.
Wrong. No. Look, remember one of the things we need to do is be able to precisely locate this? Well, in order to try to find the middle of some big square, there's like nothing there. It's all black. I wouldn't know where to land. Okay. Well, what about along the edge? Would a point along the edge be a good interest point? Megan, what do you think?
Yes.
No! Look. Okay, so if my edge was vertical, we're going to do this in a minute. If my edge were vertical, I could tell which way to move left and right. But as I move up and down, nothing would really change, right? I just have black on the one side, white on the other side, and this edge in the middle, and I wouldn't be able to tell where that point lands. Okay, you ready, Megan? 2 strikes. What about the top left-hand corner? Would that be a good point?
Yes.
Yes, she got it right. Swings and hits a home run. Well, a triple. That seems pretty good, right? The idea is that I know exactly where that point is. If I told you go point to the top left-hand corner, you'd know where it was. Whereas if I said go point to the middle of the square, the exact middle, you'd look at it and say, I don't know. You'd have to get Megan, and she wouldn't know either, and she'd say, oh, I'm sorry. Anyway, okay, so let's take a look at this. All right, so this really is the basic idea of corner detection, all right? So here I have a black, sort of zoomed in on a black kind of rounded square against a white background, where this brown little square is, right? I could move that square up and down or left and right, and basically the pixels underneath that square wouldn't change very much. That's what's referred to as a flat region. That is, that there's no change in the intensity. Well, here's our edge. Okay, so now we've put our square over the edge. So what do we see? Well, it's the same thing we talked about before. Now I can know about moving left and right. I would know exactly more or less where that edge is. But if I were to move up and down, okay, I wouldn't be able to see any difference because there would be no change. So finally, what do we get to? Aha, we get to corners, okay? And the idea is that in the corner, basically because I have gradients in more than one direction, no matter how I were to translate that square, the pattern underneath the square will change. And so I can know when I've lined up exactly where I was before, right? So there's this idea that we need the gradients to have more than one direction. So this basic idea of finding corners, in thinking about it this way, I don't know if I would say it was first introduced, but I'll say that it was most well-known introduced way back in 1988. I know some of you guys were like in diapers, and some of you were a dream in your parents' eyes, and some of you were a nightmare in your parents' no, whatever. It's a long time ago, all right? And the picture here down below is just showing you sort of a mess of corners, and they don't all look like corners, but there are places where the gradient varies. And it was created, this paper, the Alvey Vision Conference is what later I believe became the British Machine Vision Conference, and it was done by Harris and Stevens. Now, if you ask anybody about the corner detector I'm about to tell you about, they'll tell you that they're Harris corners, because that's what everybody remembers. I know an awful lot of people in computer vision. I don't know who Stevens is. So this tells you something, that if you're doing a paper with somebody, try to get your name first. Unless, of course, it's your advisor and he or she's paying for your education, in which case then, you know. But anyway, it's actually Harris and Stevens, and you can impress somebody by saying Harris and Stevens corners, but it's Harris corners. All right, so let's learn about Harris corners. So Harris corners are based on an approximation model and an error model. And here's how we do. Let's assume that we've got an image I, and right here, right? And I is the intensity image. And what we're going to do is we're going to say, if I shift that I by a little bit, by a U and a V, and I were to sum up the square over some window, how much error would I get? Okay, that's the game we're going to play. So stepping through that, I is our image intensity, so I of xy is just the original image. The U and the V is some small shift. So if I were to pick up my window and move it over a little bit, I would now get some different image, just shifted by a little bit. I subtract them and square them, and then I'm going to sum them up over some window. Okay, so the window is going to be some area around some point. So that's written here as W of xy. The total value here, E, is sort of for error. You really can think of it as sum of the change, where E for error, energy. But the idea is that we're going to sum it up around that window. Now, of course, your window can typically be a square window, like in my house, or if you want it to actually work a little bit, or on a slow computer, you make it be a square window. But if you actually want to weight the pixels near the point you're thinking about more than the pixels that are far away, you would use a window that falls off in intensity. So like a Gaussian window would be an example. So typically, your windows can be square if you need to be really fast, or smooth if you need to be really good. So are you fast or are you good? So now we can start to graphically illustrate this. So on the left, I have an image, I of xy. And on the right, I have the new function E of uv. Okay, so remember, E is the error. Okay? And what we're going to do is we're going to put 0, 0 sort of in the middle, right? So this goes plus in u and minus in u. This will be plus in v and minus in v. All right? So what if I just leave the square right in the same place? What if I make u and v be 0? How much error am I going to get? Well, none, okay? And so E of 0, 0 is 0. I'm just subtracting the same image from itself, and that's what this E00 is meant to show. Oh, and by the way, just showing you, this little pixel here is black. Why is that black? Because that's 0, right? There's 0 error, E of uv, right? Error, because it's a sum of squares, can only become more positive, right? So at 0, 0, it's going to be an error of 0. So now, suppose I move my window just a couple of pixels, like 3 in the U direction and 2 in the V direction. Now my error is going to be whatever it is, right? And over here, right, you'll notice this is now a gray value, right? Because the value has gotten higher, right? So the error grows as I move away. And just think for 1 minute, suppose that picture were perfectly gray. Every pixel was the same value. That error would be 0 at the middle, at 0, 0, and as I moved it, it would still be 0. So that should give you some idea of where we're headed. We're looking for points where, as I move in UV, I get this nice change no matter how I move in UV. Got it? Cool. So what we want to do is, we want to figure out, we want to model how this error function changes for small shifts. So we're not going to move u of 97 pixels. No, we're going to move maybe even just a fraction of a pixel, or a little small shifts right near u and v being 0, 0. That is around no shift at all. And of course, what we'd like to see is that we get a significant change even for a small shift. That would tell us no matter how we move in u and v, and that would tell us that this image is going to change as I move around, and maybe it's corner-like. So how do you predict the value of a function for small shifts? Do you remember this? Do you remember this? Oh yeah, calculus. Taylor expansions? All right. We're going to do a second order Taylor expansion of E of uv, that's our function here, around u and v being 0, 0. And the second order means it's going to be a quadratic approximation. All right, so strap in, because we're going to go through the math of doing that, and it'll get us to a point where it's very easy to compute whether the neighborhood around a point feels corner-like. All right, so you may not remember everything you need to know about Taylor expansions, so I'm going to write this out. So back when you first took calculus, this was the equation of a Taylor approximation, where we say that the value of a function of some small delta near 0 can be approximated by the value at 0 times the first derivative times delta x times the second derivative of delta squared x, half of that. That was the Taylor approximation. I'm sure you all have that tattooed somewhere on your body. All right. So it gets a little uglier when we do things in 2 dimensions. Remember, it's u and v. Okay? And we're going to write that out for this expression, this error of uv function this way. You ready? Okay, don't panic. What we're saying is that the error function uv for some small uv's near 0 can be approximated by the value at 0, 0, the first derivatives times the uv, so that's like this df of x times delta x, except now we've got it in 2 dimensions. So we've got the gradient in the u dimension plus the gradient in the v dimension. Plus, we have this quadratic term, and in vector notation for 2 dimensions, that quadratic term is written like this. So these are our second derivatives, uu, vv, this is uv, uv, and we just matrix multiply times the uv vector. Hopefully this is somewhat familiar to you from your vector calculus. If not, it's just true. So now what we're going to do is we're going to step through, bear with me, this whole second order Taylor expansion about uv of 0, 0. By the way, you guys should appreciate that I am not writing this, so you actually could read it, and there'll be PDFs presented of some sort so that you can get it from there, or you can go to Rick Zalisky's book. It's all there. But believe me, you don't want me to write this. You just want me to be humorous and lighthearted. All right. So here we have our Taylor expansion written just as before. So we're going to knock these derivatives down one at a time. We're going to start with our first derivative, right? We have to do the first derivatives and the second derivatives. So the first derivative we're going to look at, the first derivative we're going to look at is with respect to the u direction. Now u is the offset in the x direction. Okay, just remember that u is the offset in the x direction. And we're going to take the derivative of this function, e of uv, with respect to u. Okay, let's see, well, we've got the square term here, so that gives us this, we raise it to single power instead, and then we have to take the derivative of the inside term with respect to u, and let's see, there's no u's in there, that's go away. So there's a u in here, so I have to take the derivative of I of x plus u, y plus v, with respect to u. Okay? Not me, you. Okay, anyway. Well, remember, u is in the same direction as x. So the derivative of the image in the u direction is the same as the derivative of the image in the x direction. So I need the image gradient, I sub x. Got it? Good. I'm not going to do v. V is exactly the same thing, except instead of x's, you get y's. Now what we do is we're going to do the second derivative. So we're just going to take the derivative of this with respect to u. Well, there's 2 parts here, right? We've got this part, and we've got that part, right? So the derivative of a product is u times dv plus v times du, remember? Yes, 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 yes. Except u's and v's is a terrible choice because we have different u's and v's. But basically the derivative of the first times the second plus the derivative of the second times the first, what is that going to look like? That's going to look like this, okay? So we take the derivative of the part that's the image and multiply it, so that just gives us this twice. And then the second one is we take the derivative of the derivative and multiply that by the original. That gives us this second derivative. Okay? The math's pretty easy. You can work it out. This is the e with respect to u term. All right? So we've done the first derivative, the second derivative. U and v are the same. So the only thing left to do from that matrix, we had euu, evv. We need the cross derivative. And that just looks like this, where we take the derivative of the previous one, of u with respect to v now, and we get something that looks like this. And you'll notice that this has the gradient in y, the gradient in x. Remember, x is the same direction as u, y is the same direction as v. And it also has this cross derivative. We haven't talked a whole lot about the cross derivative, and in fact, we're not going to talk even more today about the cross derivative, because later we're going to make it go poof, go away, so we won't even think about it. So now we have our first derivative, u, v is the same. Our second derivative, uu, vv is the same, and our cross derivative, right? Right. So here they all are in their incredible glory. All right, so this equation is ugly, but we're going to be able to make a bunch of it go away. And the reason that we're going to be able to make a bunch of it go away is since we're going to evaluate it at u and v equal to 0, 0, we're just going to make all these plus u's and plus v's everywhere be 0, 0. Okay? Remember, we're evaluating our derivatives at 0, 0. So all of these terms that have the plus u plus v, The plus u and the plus v go away, and you get something much simpler that looks like this. Now, that still looks kind of ugly, okay, until